the uniform continuous random variable. So our goal is to differentiate basically the properties of discrete random variable and the uniform random variable. So here you can see that the function fx is non-zero. It is taking value 1 on the closed interval 0, 1, and the other place is the value of the fx is 0. Value of the fx is 0. So if we consider this PDF as a probability function and relate it to the probability mass function, then probability mass function is fx equals to probability of random variable less than or equals to x. CDF is less than or equals to x. Probability mass function is probability function P of random variable x, capital X equals to small x. Capital X equals to small x. So you can see that the value x, which is taking fx is 1, is in the positive integer, in the positive length interval, right? But if we take the random variable, which is discrete, it is non-zero at the finitely many points. Probability mass function is non-zero at the finitely many points or on the countably many points, right? So that's why this probability function is not the probability function PDF of discrete random variable. So is it clear by looking at fx, it is not discrete? So we have discussed, so we'll compare this fx with the function fx for the discrete uniform random variable. So that also we discussed in the last class. So in the last class we discussed that. So this is CDF. And what is the CDF of uniform random variable, continuous random variable? This capital Fx is a continuous function. Capital Fx is a continuous function. But when we take random variable capital X to be the discrete random variable, the corresponding CDF, cumulative function, may not necessarily continuous. So this is another property which differentiates the random variable with the continuous random variable. So here you can see that the function capital Fx 0 x minus a by b minus a and 1, that is continuous at x equals to a, because x equals to a, x minus a is 0. And similarly, if you put x equals to b, then it is b minus a by b minus a, that is 1. So at x equals to a and x equals to b, the function capital Fx is continuous. Capital Fx is continuous. It is continuous because x is not the random, not the discrete random variable. X is not the discrete random variable. So this case, this example, we discussed that. Okay. So this is limiting case. We discussed that it is a limiting case of uniform continuous random variable, that is limiting case of finite discrete random variable uniform. And then we discuss normal random variable that is given in this way, and we can substitute values of sigma and mu. So this function, the density function depends on two parameters, sigma and mu. So we change sigma and mu, we get the different normal random variable, different density function. So this function is symmetric around the vertical x equals to 1 line. And then we have discussed Moivre-Laplace limit, that says that it is a limit of this yn. So that is coming from the binomial discrete random variable. It is coming from the binomial discrete random variable. Okay. So then we are discussing the distribution function. Distribution function is defined for two cases. One when capital X is discrete random variable. The other one is capital X is a continuous random variable. So whenever it is a continuous random variable, we have capital Fx x is area, that is integral minus infinity to x small fx t dt, where small fx t dt is a mass function PMF. And when x is a discrete random variable, we need to add the value capital f of capital X t for t less than equals to x and t is in the range of x. So if range of x contains different values, that many non-zero values we have fxt, right? Non-zero values fxt. So they are exactly the jump discontinuity value at that points. So we have seen such example, the discrete uniform random variable, which takes n values, 1, 2, up to n, and we can see that here the function is not continuous. Capital Fx is not continuous. So now you can see that if we know capital Fx, we can judge whether our random variable x is discrete or not, whether our random variable is discrete or not. So here the capital Fx function is given in this way: 0, 1 by n, 2 by n minus 1 by n, and 1. Right? So we can see that the function, the left limit at 1 is 0, but at 1 capital Fx is 1 by n, 1 by capital N. If the parameter n is 20, this value is 1 by 20. Capital Fx at 1 is 1 by 20. Right? So there are exactly n points, 1, 2, 3, up to capital N, where the function is left discontinuous. Capital Fx function is left discontinuous. And all those points, exactly we get the probability mass function non-zero. Probability mass function non-zero. And at other points, the probability mass function is value is 0. The probability mass function value is 0. So what does this example gives us information that if we know CDF, we can find PMF, and then we can have some information about the random variable. So if we have this CDF, suppose it was not given that x is a discrete random variable, uniform random variable. Suppose we are given only this function capital Fx, which is 0 for x less than 1, 1 by n for 1 less than equals to x less than 2, and so on up to 1 in this way. Then by looking at CDF, we can actually find PMF. And since the PMF is non-zero at only finitely many points, 1, 2, up to capital N, the corresponding random variable is discrete. Because that is the characterization of PMF. If you recall, we have studied that the PMF of discrete random variable satisfies three properties. Small fx is non-negative, small fx is greater than 0 is a countable set, and the third property is summation of fx, all the values fx greater than 1, the total is 1, total probability is 1, that is summation fx is 1 for all x is in the range, all x in the range for which fx is positive. So here you can see that the elements x for which probability mass function is non-zero, at those points value of small fx is 1 by n, 2 by n, n minus 1 by n. When we add that, it's a difference. Yeah, so it's a difference. So small fx, so let me write something. So suppose this function is given in this way, and it is given that what is the random variable? What is the random variable? So whether it is discrete or continuous, so we directly find small fx at x. So at 1, what will be its value? Its value will be the left limit. We need to subtract from the value of at 1, right? So what is the left limit? Left limit is 0 plus 1 by n. Similarly, fx at 2 is 2 value is 2 by n minus 1 by n. So that is 1 by n. So at each point, the probability mass function is 1 by n. So total probability is 1, because there are n points where mass function is non-zero, and each point the probability is 1 by n. Total probability is 1. And then we can understand that the probability is equal at n points. That means the random variable is discrete random variable. Okay, so we have also seen this example of Bernoulli trials, and okay, and then we discuss some other examples. So these are the properties of CDF, which we discussed 3 properties in the last class. So it should be non-decreasing function, and at x tends to minus infinity, its value should be 0. Limit x tends to infinity, capital Fx should be 1, and it should be right continuous. It may not be left continuous, but it is always right continuous. So we proved these properties, and these 3 properties characterize CDF. And then we discuss this example by, so we essentially use that the derivative of CDF is PMF when the function is differentiable. Capital Fx is differentiable. That means integrand is continuous. Okay. So today we want to discuss some more examples and some more properties. So what is our goal is in today class is we want to go to PMF from CDF, right? So that is what exactly I explained, CDF to PMF. So if one function is given, we can find the other function. So we can relate CDF with PMF, PMF with CDF, and then we can identify whether given random variable which assigns each outcome to a real number, that is whether it is discrete or it is a continuous. So discrete case, we studied certain examples of discrete random variable, that is binomial, uniform, discrete, Bernoulli, geometric. Right. So these are the examples. And on the other hand, for continuous, we have discussed uniform continuous on the on an interval, uniform continuous random variable over the interval. Okay. So the question is that we have discussed that probability of random variable capital X less than equals to small x is essentially CDF. So today we will show that if we take probability of capital X strictly less than x, then that is essentially the left limit. So let x be a random variable, and capital F is the distribution function of the random variable x. Then we show that the left limit of the distribution function at the point x is essentially probability of random variable taking value less than x, taking value less than x. So what is this symbol? We already know this is the left limit. So earlier also I mentioned that capital F is given, then capital F means CDF. And if you say just a distribution function or density function, that means we are discussing CDF. We are discussing CDF. Okay, so we want to show it left limit value of the CDF is essentially probability of x less than x, x less than x. So again, we are going to either we can prove this using the area, or we can prove it using the properties of probability function P, probability function P. So now similar result we discuss for the right limit, right? So for the right limit exists because capital Fx is continuous on the right side. So it is value of the function at that point, value of the function at that point. But left side we are saying only that the left limit exists. We are not saying that the value of the left limit is value of the function. We are only saying that probability of x less than x is a left limit. So left limit exists for the distribution function. So let us start with the, again we'll take sequence approach. So since we have left limit, we are taking xn, which is a sequence of real number which increases to c, and we want to show that capital Fxn converges to this value. Capital Fxn converges to this value. So note that since we have numbers x1, x2, xn which increases to c, that means the event random variable taking value less than x is essentially union of the events less than equals to xn, all right? Because okay, so let me call this value x. Yeah, so this value is x. So xn increasingly convergent to x, then the union of all xw less than equals to xn, those w. So is it clear these two sets are same?
Yes, sir.
Right, because each x less than equals to xn, each w such that xw less than equal to xn is already xw less than equals to x, is less than equals to x, and for some value w such that xw less than x. So since xw less than xw is on the left side of x, that means there must be n such that xn will be in between xw and x, because xn converges to x. So therefore these two sets are same. So these two events are same. And then we know the probability function P whenever we have, so this x less than equals to xn is an increasing events. Yeah, that is a increasing sets. So A1 subset of A2, subset of A3 in that way. So it is increasing sequence of set. So we can use the probability function property. So therefore probability of x less than x is exactly probability of union, and these are the increasing sets. That means we can use the limit theorem. So that is limit of probability of x less than equals to xn, x less than equals to xn. And then what is this function? This is essentially the CDF. This is essentially the CDF at xn, at the value xn. So that is capital Fx at xn, limit n tends to infinity. Limit n tends to infinity. So xn is an increasing sequence which converges to x, and capital Fx is the function which is monotonic, So therefore, limit n tends to infinity capital Fx n, capital Fx at xn is basically the left limit at x. Because Fx is monotonic. Fx is monotonic, so that is the reason why we have this is a left limit. So left limit is essentially probability of capital X less than x, capital X less than x. So left limit always exists, but we are not saying that remark. The above theorem gives value of left limit, which in general may not equal to capital Fx at that point, right? So left limit exists, but limit may not be the value of the function. That means we are not saying that it is left continuous function. It may or may not, depending on what is the capital Fx. What is the capital Fx? So one immediate corollary of this is that we know that if we have a monotonic function, it can have discontinuity at only countably many points. It can have discontinuity at only, at most, countably many points. So it can have that function which is monotonic. It may be continuous also. So no discontinuity, or it can have one discontinuity at one point, n points, or countably many points. But it cannot have discontinuity at uncountably many points. So, so every distribution function can have jump discontinuity which is essentially coming from the left continuity, and at most countably finitely many. So basically finitely many points is a subset of countably many points. So let us write countably So reason is that it is monotonic. It is monotonic function. Okay, so this is the property of the monotonic function which cannot have discontinuity for more than countably many points. So now we have seen examples. We have seen examples in the last class that we actually written the probability mass function of the uniform variable, which is essentially continuous function, which is essentially the continuous function. So you can see that this function is continuous. Capital Fx is continuous function. So there is no point where it is not continuous. So no discontinuity points. So uniform continuous is the case where it is continuous. It is continuous. Similarly, uniform discrete we have discussed, which is discontinuous at n points. It is discontinuous at exactly n points. So why this we can have one remark. So we can easily check and observe that number one, that CDF of continuous uniform exponential and normal random variable are continuous functions. Right. So there is a unique CDF, so it is a continuous function. Second remark is that there are certain discrete random variables for which we have discontinuity at finitely many points. So they are Bernoulli and binomial. So Bernoulli and binomial. So Bernoulli, I think we have checked in the last class that it has discontinuity at 2 points. So binomial CDFs have discontinuity at finitely many points. And the third one is it can have at countably many points. So one example we will discuss is geometric. And Poisson. Just a minute. So geometric and Poisson random variables have geometric and Poisson random variables have CDFs which is discontinuous at countably infinite sets or points. Okay, so essentially what this remark is saying is that, note that this remark and the last theorem says that whenever we have the above proposition, simply means that if you want to find the probability mass function, then probability mass function is probability of capital X less than equals to X minus probability of capital X less than X, capital X less than X. Right, because we are going up to value X including X minus probability of up to X less than X. So the only point remaining is X, that is the probability mass function. And then we know that what is the probability of X less than equals to X, that is capital Fx, CDF. So that is CDF value at X minus left limit at X, left limit at X. So whenever the left limit is exactly value of the Fx at X, that means it is left continuous. The probability mass function at that point is value is 0. Value is 0. But every time it may not be left continuous, that means every time P may not be 0. So P takes only two types of value, either 0 or positive value. 0 or positive value. So this is the formula, it gives PMF using CDF. So value of PMF using CDF. So example, if you have the function whose distribution function is given we want to identify whether the variable is random or not. And to identify whether the variable is random or not, we need to find its PMF, right? We know the property of PMF of the discrete random variable. There are characterization of PMF for the discrete random variable. And whenever the variable is not discrete, we get the PMF identically 0. PMF identically 0. That means capital Fx function is continuous. Right? Again, I am repeating. Capital Fx is a uniform discrete random variable. Then we have checked that it is continuous everywhere. Continuous everywhere. That means its PMF is identically 0. Its PMF is identically 0. Okay, so so first example, that suppose x is a random variable with the distribution function capital Fx to be taking 4 values 0, 1 by 4, 3 by 4, and it should go up to 1, right? So for x less than 0, value is 0. In the interval 0 to open 1, the value is 1 by 4. The value is 3 by 4 for 1 less than equals to x less than 2. And otherwise, that means x greater than 2, greater than or equal to 2, the value of the density function is 1. Value of the density function is 1. So question is determine whether x is a discrete random variable. And we know that if it is a discrete random variable, we can identify using the probability mass function, and we can actually find that using the left limit. We can, so if yes, find its PMF. So how we will get to know whether it is discrete or not?
Sir, check the limits at seem to be discontinuous points.
Right. So left discontinuous points we need to identify if that exists or not. So what are the possible points? So here the value is 0 on the left side, 1 upon 4 on the interval 0 to 1, 3 by 4 in the interval 1 to 2, and 1 after 2. So essentially there are 0, 1, and 2, 3 points, which is essentially dividing the real line. And on the interval, values are 0, 1 by 4, 3 by 4, and 1. They are constant functions. So on the intervals, this function is continuous. So only we need to check at the endpoints 0, 1, and 2. So 0, what is the left limit? Left limit is 0. And x equals to 0, the value of the function is 1 by 4. So at 0, the function is capital F is not left continuous, right? You can see it is always right continuous because the way we are defining 0 less than equals to, 1 less than equals to, and 2 less than equals to. So therefore, capital Fx function is it should be right continuous. So in this example, it satisfies that property. So what is the characterization of distribution function? It should be right continuous. At x tends to minus infinity, it should be 0. At x tends to plus infinity, the value of the function is 1. And it is a monotonic function. So these capital F functions satisfy all the properties of distribution function. So first of all, it is a distribution function. Second thing, we need to check whether it is a discrete distribution function or it is a continuous distribution function. So what is the corresponding random variable property? So for that we need to check that the left continuity. We have checked that at 0 it is not continuous. What about at 1? Again it is not discontinuous because left limit is 1 by 4. The value of the function is 3 by 4 at x equals to 1. And similarly at 2 also the function is not continuous. So at three values the PMF is non-zero. PMF is non-zero. And what is the addition of these values? So 1 by 4, that is the difference between left limit and the value at 1 by 4. Let me write down. So first of all, note that f satisfies three properties of CDF, right? So it satisfies the characterization. Therefore, it is a distribution function. Now we need to check whether it is corresponding to the discrete random variable. So also note that f0 minus is 1 by 4. f1 minus f1 left limit is 3 by 4 minus 1 by 4, that is half. And f2 minus left limit at 2 is essentially 1 minus 3 by 4, that is 1 by 4. Right. So since this function, the probability mass function becomes positive at certain points, at 3 points, at countably many points. So that means it is possible that this variable is discrete random variable, right? Because if it is uniform continuous random variable, the probability mass function will be 0. At the endpoints. But here it is non-zero. And the second thing is that we need to check the three properties. So other points, the probability mass function will be 0. So what is this value? This is probability of x equals to 0, that is fx at 0. This is probability of x equals to 1. So if this probability mass function small fx is corresponding to the random variable x, which is discrete, then the total probability should be 1. So 1 by 4 plus half plus 1 by 4, the total should be 1. And that is the case because 1 by 4 plus 1 by 2 plus 1 by 4 is 1. Right. So at the points, there are 3 points where PMF is non-zero. The value of all the PMF, where it is non-zero, the sum should be 1. Right. So these are the properties of PMF, which is satisfies PMF of the discrete random variable, that is satisfied by the PMF of this function corresponding to the capital F function. So therefore, small fx is a PMF and the corresponding variable is a discrete random variable. So therefore, the x corresponding to given capital F function is a discrete random variable. So can you recall what is the corresponding x which satisfies these properties? We have discussed this example when we discuss probability mass function example in the beginning, when we have the random variable which takes value 1 by 4, 1 by 2 and 1 by 4. So what was that random variable?
So number of heads.
Correct. So that is a number of heads. So either 0 head. So we have we need to toss a coin 2 times. Toss a coin 2 times. So outcomes are HH, HT, TH, and TT. So there are 4 outcomes. So uniform probability is 1 by 4. Uniform probability is 1 by 4, and getting getting 0 head, that means the corresponding event is HH. Sorry, TT, and that has probability 1 by 4. Getting 1 head is HT and TH, probability is 1 by 2, and getting 2 head is HH. So that is the event is HH, its probability is 1 by 4. So this is a discrete uniform random variable with essentially 4 outcomes. Essentially 4 outcomes, and the experiment is that. So good. So this is related to that particular discrete random variable. So now you can see that here we have no experiment was given. We were given only CDF. So using the property of CDF, we have identified which experiment, that means which random variable we are discussing. Okay, so it is kind of converse properties. Converse properties. Okay. So this is the first example. The next example we want to discuss is suppose we are given, consider the following distribution function, that is capital Fx to be 0 if x is less than 1. It is taking value 1 minus p power k if k is between x and k plus 1, x and k plus 1, where p is any positive number and k is equals to 1, 2, 3 up to so on, right? So what we need to do, we need to determine its PMF. So the way the question is given, you can understand that 0 less than p less than 1, and we are given the intervals which are dividing by the integers 1, 2, 3 and so on. So the last condition which is given, that k less than equals to x less than k plus 1, if we take k is equals to 2, then the interval is 2 less than equals to x less than 3, and in that case the value of capital Fx is 1 minus 1 minus p square, because k is 2. So similarly, so basically this function is essentially defined on the intervals 1 to 2, 2 to 3, 3 to 4, right? So in that way, so therefore it is defined everywhere on the real line, but we don't want to write all the intervals separately, 1 to 2, 2 to 3 and dash dash dash. So therefore we have written using iteration formula for the interval close k to open k plus 1. So so is this capital F function satisfies all the properties of CDF? So p is between 0 and 1. So 1 minus p is also between 0 and 1. 1 minus p is also between 0 and 1. And if you take any number between 0 and 1, its square will be less than that, right? When p is greater than p square is greater than p power 3 and so on. So we can use that property and easily see that f is a monotonic function. And at k is equals to 1, the value is 1 minus p. So 1 will cancel, and that is exactly p, value is p. So okay, so in that way we can see that the function may not be continuous at x equals to 1. In fact, it is not continuous at x equals to 1 because p is between 0 and 1. So at x equals to 1, the left limit is 0, right limit is p. Right limit is p. So let me write down what are the general at every k. So for each natural number k, the value of the mass function essentially is fk minus fk minus 1, the left limit at k. So fk, we know fk is this value at the point k. So that is 1 minus p power k. And what will be the left limit? So that will be, so one more thing we can write down, that is, so at this point the value of the function is k plus 1. Right. So at any point the the value of the function is this and the left limit is this. So difference of k, one difference will be there. Right, one difference will be there. So if you write down this, the value of the function is this. When we find the left limit, it is 1 power less, so k minus 1, right? And then we take the difference of these two terms, 1 will cancel out, and essentially we get 1 minus p power k minus 1 minus 1 minus p power k, right? So this minus this minus this, and then we can take 1 minus p power k minus 1 common, so 1 minus p, that is exactly p, right? So do you recall that which random variable satisfies the property of this PMF?
So geometric.
That is a geometric series, right? Geometric random variable, which is a discrete random variable. So probability of getting head is p, and we are tossing the coin up to getting one head, one success. So the failure probability is 1 minus p, which is q, and that is q power k minus 1, q power k minus 1. So this random variable, first of all, using this this CDF, we have found this PMF p of x equals to k, and when we add this p of x equals to k, we know that the sum is 1, and each px equals to k is positive. So this capital P satisfies. So what is this capital P? Basically small fx. So the small fx satisfies all the properties of PMF for the discrete random variable, because it is non-zero at countably many points, and its sum is 1 because of the geometric series properties. So therefore fx, the x corresponding to this distribution function satisfies all properties of not x the PMF satisfies all the properties of discrete random variable. So therefore random variable is discrete, and indeed we can observe that. We observe that this is PMF of geometric random variable. So we are given PMF, we know how to find CDF. In these examples we are discussing, if we are given CDF, what is the corresponding random variable, and then depending on that we find the PMF function. Depending on that we find the PMF function. So these are the simplest examples. So now we have CDF to PDF in the continuous case. So whenever we have a continuous random variable, we have a continuous random variable. Now, so discrete random variable, as I said, it satisfies the probability mass function, satisfies it is probability mass function is positive at finitely many or countably many points. But continuous random variable, we know the CDF of uniform continuous random variable over the interval, and the CDF of continuous random variable is a continuous function. It is a continuous function. So since it is continuous, it is left continuous at every point, left continuous at every point. So therefore its PMF is identically zero function. Its PMF is identically zero function. So whenever capital Fx is continuous, what we will do, we know that whenever capital Fx function is continuous, it is defined integral x to minus infinity ft dt. So whenever to get small f from capital F, we need to differentiate the function. We need to differentiate the function. So whenever Fx is equals to probability of x less than equals to x, which is minus infinity to x ft dt. This function is continuous. Using fundamental theorem of calculus, we get so what we get? We get Fx, which is essentially derivative of x whenever capital Fx is differentiable. Whenever capital Fx is differentiable. So that is directly we get from this criteria. And the another thing is also, if f is continuous everywhere, then the corresponding random variable satisfies Fx is 0 at the points where f dash x does not exist. So what do we mean by this? What do we mean by this? So let us take one example. So we have a distribution function. So consider Fx to be 0, x and 1. 0, x and 1 for x less than equals to 0, for the value 0 less than x less than equals to 1, and for the value x greater than 1. For the value x greater than 1. So determine whether x is a corresponding random variable x is discrete or not. And accordingly find its PMF or PDF. Okay. So now the function given is this function. So at which points this function is differentiable? So on the left side it is 0 function, so it is a constant function, it is differentiable. In between 0 and 1 it is the function, identity function fx equals to x, so it is a differentiable function, derivative is 1. On the right side of x the function is again constant function 1, it is differentiable. So only possible points where it is not differentiable, it 0 and 1 we need to check. So at 0 and 1 are the possible points, x equals to 0 and x equals to 1 are the possible points where f is not differentiable. That means f may not be differentiable, right? We are not saying f is not differentiable, f may not be differentiable. So let us check. So to check that we need to check the left derivative and right derivative. So observe that the left derivative at 0 is essentially 0 plus h minus f0 and h, which is limit h goes to 0, 0 plus 0 by h, which is 0, because on the left side the value of the function is 0. The value of the function is 0. What about the right limit? So right limit, we have the function identity function, identity function, so that is h minus 0 by h, and that is essentially the value is 1, because h by h is 1 and the limit is 1. Similarly, limit h tends to 0, f of 1 plus h minus f1 by h, that is basically limit h approaches to 0, 1 plus h minus 1, because the function is identity function, and at 1 the value is 1 divided by h. So again the value is 1, and the other limit is on the right side, the value of the function is constant function 1, the value is 0. So these two are different, so it is not differentiable at 1. These two are different, so not differentiable at 0. So f is differentiable except points x equals to 0 and 1. Okay, so at these points, let us write down the derivative. What is fx at x? That is essentially the derivative at x, derivative of x. So derivative function we can write at 0 if x is less than 0, 1 if 0 less than x less than 1, and 0 if x is greater than 1. So now you can see that the probability mass function is 1 at uncountably many points. So at which point it takes value 1? Over the open interval 0 to 1. Right? We have not checked at 0 and 1. We have not checked at 0 and 1. But what we know is that this variable is almost looking like uniform random variable over the interval 0 to 1, because uniform random variable over the closed interval AB is 0, x minus a by b minus a, and 0, that function. So when we take the interval AB to be 0, 1, a is 0 and b is 1, that means the function is 0, x and 0, so derivative is 0, 1 and 0. Derivative is 0, 1 and 0. So this is almost looking like the uniform random variable. Only thing missing is values at 0 and 1. And we know that if we define uniform random variable over any interval, close interval a to b, open close interval a to b, or close open interval a to b, or close interval a to b, the uniform random variable, the area is same. What is the reason? What is the relation of value at the endpoints and the integral? So if we
Sir,
change,
value of integral is difference of the values at endpoints.
no, what I'm saying is that so when did we define the uniform discrete random variable? Let me go to that. So look at this function. Look at this function. Yeah. So if we change this function at the point small fx function, look at this function small fx. So if we change the small f function at the endpoints, so what is this function? This function is essentially, let us go here. Okay. So let us draw the graph of this function. The graph of this function small fx is essentially 0 to 1, 0 to 1, and the other points. So okay. So on the left side, the value of the function is 0. In the interval 0 to 1, the value of the function is 1. On the right side, the value of the function is 0. So what will be the capital Fx? Capital Fx at x is integral minus infinity to x fx at small x small t dt. Small t dt. Right. So we know this integrand function accept its value at 0 and 1. Accept its value at 0 and 1. So if we define any value at 0 and 1, what will be its impact on the integral? Value of the integral. So whether it will change the area?
No, sir.
Will not change the area. Right. So therefore, whatever value we define at 0 or at 1 of the function small fx, it will not change the area, and therefore it will not change the CDF. It will not change the CDF. So the corresponding CDF of the function, what we want to say is the CDF of the uniform discrete random variable over the interval 0 to 1. Over the interval 0 to 1. So note that here fx is non-zero at uncountably many points. So therefore, it is not a discrete random variable. In fact, it is a further, capital Fx is essentially CDF of uniform random variable over the interval 0 to 1. So therefore x is continuous random variable u01. So we have written u close 0 open 1, but it is same as u close 0 close 1, and it is same as u open 0 close 1, and it is same as u open 0 open 1, because what is the value of the function at the endpoints, it will not impact the area, it will not change the area. So all of these u has the same distribution function capital Fx, has the same distribution function capital Fx. So this is the example which is different from the earlier example, because here we are getting the probability function, probability mass function is non-zero at the uncountably many points. So it is not discrete random variable, and we have checked it is a, in fact, uniform random variable. Uniform random variable. Okay, so there are some examples where the capital function f function is differentiable everywhere. Is differentiable everywhere. So such a example is that, so let x be the random variable with the distribution function fx to be 1 upon root 2 pi, 1 upon root 2 pi minus infinity to x e power minus t square by 2 dt. So in fact, from the formula itself, it is clear that which random variable we are discussing. So the formula is essentially the CDF of the normal variable, normal random variable, right? So the important point to note this is that here the integrand e power minus t square by 2 is continuous everywhere, continuous everywhere. So in the earlier example, the value was given in terms of value at each point x, but here it is given explicitly in terms of the integration, and in terms of the integration, if such a function is given and the integrand is continuous, if the integrand is continuous, then we can directly differentiate it. We can directly differentiate it using the fundamental theorem of calculus. So therefore, its derivative, that is ft is derivative of fx at t, and that is essentially the value of the integrand at x, value of the integrand at x. So that is, so here actually the integrand is along with root 2 pi, so the derivative is 1 upon root 2 pi time e power minus x square by 2. So okay, so in terms of t, it is t square by 2, t square by 2. So using fundamental theorem of calculus. Okay, so now the last example which we want to discuss. So we have mentioned earlier that if you have a random variable x and y, any variable of the form ax plus by is also a random variable. So combination of random variable is also a random variable. So it is essentially the vector space. It is essentially what we are seeing is a subspace or a vector space property. So let us consider one random variable example. So x is a random variable. Consider the distribution function so we have a distribution function capital Fx, which is essentially taking value 0 for x less than 0. It is taking value x square for 0 less than equals to x less than half. It is taking value 3 by 4 if 1 by 2 less than equals to x less than 1, and 1 if x is greater than equals to 1. So this is the CDF we are given, basically the probability density function or distribution function. So the question is what type of what is the type of the corresponding random variable x. So basically we want to identify whether it is uniform or discrete random variable, and accordingly find PMF or PDF, and further compute the value of the probability of x taking values between 1 by 4 and 1. 1 by 4 and 1. Okay, so solution is essentially we want to see that the function is, by looking at the function, it is continuous everywhere except the points half and 1, because half left limit is 0, the value of the okay, so at 0 it is continuous because left limit is 0, value of the function is also 0, and at half the left limit is 1 by 4, value of the function at half is 3 by 4, and at 1 the left limit is 3 by 4, value of the function is 1. So 2 points we have. So fx at half, fx at half, that is p of x equals to half, is f at half, because it is left discontinuous, it is value of p x equals to 2 is f at half minus left limit at half, left limit of capital F at half, that is 3 by 4 minus 1 by 4 is half, and probability as at x equals to 1, probability at x equals to 1, just 1 minute, probability of, okay, so fx at 1 is probability of x equals to 1, which is essentially f1 minus left limit at 1 of x, and that is value of the function at 1 is 1 minus 3 by 4, which is 1 by 4, right? 1 minus 3 by 4, that is 1 by 4. So what two values we got? Non-zero values is half and 1 by 4, is half and 1 by 4. All the other points, okay. So what is the derivative of the function on the intervals? Derivative of the function on the interval is 0 except on the interval 0 to half. So on the interval 0 to half, the derivative is 2x, derivative is 2x. So if you recall how to find the value of fx on the interval, so that is essentially the probability given, so integral 0 to half essentially, so that is probability of 0 less than equals to x less than half. So that is integral of small ft this interval, that is 0 to half small ft dt, small ft dt. And then we integrate this, we get the value is 1 by 4, 1 by 4. So now you can see that half plus 1 by 4 plus 1 by 4, total is 1. Total value of the total probability is 1. Value of the total probability is 1, but it is not the discrete random variable because fx is non-zero at uncountably many points. So in particular on the interval 0 to half, it has the value x square. So value of the small fx is non-zero over the interval 0 to half. That is uncountable set. So therefore, x is not the random variable. It is also not the uniform random variable because on the interval 0 to half, the value of the probability is 1 by 4. Value of the probability is 1 by 4. Right. So this is not okay. So this is neither discrete random variable nor uniform, nor continuous. Because if it is a continuous random variable, it cannot have the point mass. That means if it is a continuous random variable at half, the value of the probability at the point half cannot be positive. It should be positive over the interval only. Right. So essentially these 2 points, 1 by 2 and 1 by 4, contribute a particular random variable, and the other random variable is over the random variable interval 0 to half. So you can see it as a combination of these two variables. 1 by 4 plus 1 by 2 times the random variable y, which is discrete random variable, and plus 1 by 4 times the continuous random variable. So it is kind of combination. So what we have observed here is this random variable is neither discrete nor it is continuous random variable. And the last thing which we want to compute, that is we want to compute the probability of 1 by 4 less than equals to x less than 1. So that is essentially the left limit of capital Fx at 1 minus probability of x less than 1 by 4. So if you know these two left limits, we can find these. So f of 1 minus f of 1 by 4 minus. So left limit at 1, left limit at 1 by 4, difference of that, and you can verify that is 11 by 16. 11 by 16. So we know capital Fx, so you can easily find the left limit at 1 and that number. In fact, we have found it somewhere here, 1 and 1 by 4. So just verify that this value is 11 by 16. 11 by 16. Okay, so let me stop here.